What if I told you that one of the most powerful technologies of our time does not actually think the way we do, but it can write, explain, translate, code, and even hold a conversation with us? Assalamu alaikum everyone. I am Sumaia Shimu. Today I will be discussing one of the most powerful language model, that is Generative Pre-trained Transformer, abbreviated as GPT. Every time we ask ChatGPT a question, we are interacting with a language model, a system trained to understand and generate human language. And among the most influential examples of technology is GPT, or Generative Pre-trained Transformer. But what actually is GPT? How can a machine predict that word should come next? How does it learn the patterns of human language? And how did a simple idea of predicting text evolve into systems capable of generating remarkably human like responses? Today, let's go behind the conversation and understand the technology that makes it possible, like GPT. In the next 6 to 7 minutes, I will guide you through the five essential aspects of GPT. First, the transformer architecture that underpins it. Second, the autoregressive generating model objective as its heart. Third, the two-stage training methodology, which encompasses unsupervised pre-training followed by reinforcement learning from human feedback. Fourth, the scaling laws that propel its advancement and emerging capabilities they unveil. Fifth, the practical applications and the limitations that we must address with care. With this roadmap, let's dive into what GPT truly encompasses. Let's start with the basics. GPT stands for Generative Pre-trained Transformer. Each word matters. Generative means the model produces next text rather than just classifying or scoring it. Pre-trained means it is first trained on a massive text corpus before any task-specific tuning, and transformer refers to the neural architecture introduced by Vaswani and colleagues in 2017. OpenAI released in GPT-1 in 2018 it 117 million parameters. Then GPT-2 in 2019 with 1.5 billion, GPT-3 in 2020 with 1.75 billion, and GPT-4 in 2024. A steady march of scale. Pre-training uses next token prediction. Give a sequence of tokens. The model learns to predict the next one. Crucially, this is self-supervised. No human labels are required. The corpus itself supplies the signal. After pre-training, the model is fine-tuned on instruction response pairs and further aligned with human preferences using RLHF. The result is the technology behind ChatGPT, OpenAI Codex, GitHub Copilot, and a wide ecosystem of generative AI products. Let's begin with the architectural foundation, the transformer. The transformer architecture revolutionized the field of natural language processing by introducing self attention mechanisms. This innovation allows the model to weight the importance of different words in a sentence when forming an understanding, enabling it to capture complex dependencies and relationships within the text. Unlike previous models that relied heavily on recurrence, the transformer processes entire sequences simultaneously, which significantly boosts computational efficiency. At the heart of the transformer are layers of attention head and feed neural networks. Each attention head computes a weighted sum of input features, with the weights determined by the relevance of each word to the others in the sequence. This mechanism is pivotal a mechanism for understanding context, which is crucial for generating coherent and contextually accurate responses. Additionally, the architecture employs position encodings to retain the order of words, as it poses input data in parallel rather than sequentially. This combination of self attention and positional encoding allows transformers to excel in tasks require nuanced language understanding. Transformer models have been an instrumental in advanced machine translation, summarization, conversational agents. Their scalability and adaptability have laid the groundwork for the expansive growth of language models like GPT, which continue to push the boundaries of what AI can achieve in understanding and generating human language. The breakthrough that GPT made possible came in 2017 when Visoni and colleagues published the paper titled Attention is All You Need. Before this work, sequence modeling was dominated by recurrent neural networks and LSTMs, which process tokens one at a time, were slow to train, and suffered from vanishing gradients on long sequences. The transformer replaced recurrence with self-attention, a mechanism where every token computes weighted relationship with other tokens in parallel in a single matrix operation. Multi-head attention extends the several running attention mechanisms in parallel, letting the model simultaneously focus on different relationship patterns, syntax, co-reference, semantic roles, and so on. Because the model no longer rely on hidden state, passed step by step, positional encodings are added to inject sequence order information without recurrence. The original transformer is an encoder decoder architecture, but GPT uses only the decoder stack, a design choice we will cover next. The practical impact was enormous, up to 10 times faster training, which is what enabled the scale that makes GPT possible. Now let's see how the decoder only design derives text generation. The decoder only architecture in GPT, Generative Pre-trained Transformer, is specifically tailored for the task of text generation. By focusing solely on the decoder stack, GPT leverages the strengths of self attention to predict the next word in the sequence based on the preceding context. The autoregressive approach is effective because it allows the model to generate coherent and contextually relevant text by building upon each token step by step. In this setup, each token is proceed in parallel during training, which significantly enhances efficiency. The self attention mechanism enables the models to dynamically weigh the importance of different parts of the input, capturing long range dependencies and nuanced linguistic features. This capability is crucial for generating human like text as it allows GPT to maintain context over extended passages, produce outputs that are both logical and engaging. Moreover, the architecture's scalability has been pivotal in its success. By training on vast amounts of diverse data, GPT has developed a rich understanding of language, which is applies to a wide range of applications from creative writing to customer support. The model's ability or to fine-tune itself to specific tasks further enhances its versatility, allowing for fine-grained control over the text generation process. Overall, the decoder only design in GPT has revolutionized how we think about and how we interact AI generated tricks, setting a new standard for linguistic creativity and computational efficiency. Next, GPT uses only the decoder portion of the original transformer. This is what we mean by decoder only architecture. The model learns a single, depictably simple objective predict the next token given all the tokens that came before it. By the chain rule of probability, the joint probability of an entire sequence factorizes as the product of conditional next token probabilities. P of x 1 through xn equals the product over t of p of x of t given all tokens less than t. To make this work, the model applies causal masking, a triangular mask that sets the attention weights for future positions to negative infinity before the softmax. So each token cannot peek at any token that comes after it. This is essential because at interference, the time the model generates one token at a time, so the training must minor that left to right structure. For example, given the cat sat on the model learns assign high probability to mat. At GPT-3 scale, this means 96 transformer layers and 175 billion parameters working together. But raw next token predict alone doesn't make a helpful assistance. That's where the two-stage training paradigm comes in. Let's turn to the two-stage training paradigm, the recipe that turns a raw next token predictor into a helpful assistant. Stage 1 is unsupervised pre-training. We feed the model trillions of tokens from web pages, books, and code, and the only training signal is predict the next token. This is self supervised. No human levels are needed, and it is where the model acquires language, word knowledge, and reasoning patterns. Stage 2 is supervised fine tuning or SFT. We use curated instruction response databases so that model learns to follow instructions rather than just continue next. Stage 3 is reinforcement learning from human feedback, RLHF, as proposed in the Instruct GPT paper by Outwing in 2022. Humans ranks multiple model outputs. A reward model is trained on these rankings, and then PPO, proximal policy optimization, optimizes the policy agent, that reward model. RLHF is what makes ChatGPT helpful and safe rather than a raw text completer, allowing responses with human intent. But what made GPT truly surprising was how its capabilities scaled with size. Now, in scaling, in 2020, Kaplan published their influential scaling loss paper showing that model loss decreases as a smooth power law with model size, dataset size, and compute. This relationship is predictable. Bigger is reliably better, and the field took it seriously. GPT-1 had 117 million parameters in 2018. GPT grew to 1.5 billion in 2019. GPT-3 jumped to 175 billion in 2022, and GPT-4 is estimated at roughly 1.8 trillion parameters in 2023, likely using a mixture of experts architecture. Two striking capabilities emerged. Few shot learning means the user provides a few example input output pairs directly in the prompt, and the model performs the task with no weight updates at all. Zero shot learning goes further. Just in natural language instruction like translate to French, hello. Then in 2022, documented emerged abilities, capabilities that appear suddenly at a scale and are absent in smaller models. Multi-digit arithmetic chain of thought reasoning and code generation. These capabilities translate directly into real-world impact and real-world risk. Now we pivot from theory of practice. GPT has reshaped many industries. Applications span context creation, marketing, and articles, creative writing, summarization, code generation, where GitHub Copilot serves millions of developers, and OpenAI Codex powers automated refactoring and test. Customer support chatbots at scale, education tutoring, research assistance, and multimodal extensions like GPT. 4B for vision and GPT-4o for voice. But real-world deployments also exposes real limitations. Hallucinations are the most visible. The model confidently generates plausible sounding but factually wrong claims because it has no grounded truth source. It predicts likely tokens, not verified facts. Bias amplification is another task. The model inherits and can amplify biases present in its training data. There is also a knowledge cutoff. The model has no access to real time information unless augmented with retrieval. That's why safety guardrails matters. Content filters at input and output, RLHF alignment to refuse harmful requests, and red teaming, where researchers actively probe the model for vulnerabilities before release. Let me wrap up with some key takeaways. In closing, let me recap the five dimensions that we covered today. First, the transformer architecture replaced recurrence with parallel self attention, enabling scalable training on modern hardware. Second, GPT's decoder only auto-regressive design with causal masking powers, next token generation across completion, translation, summarization, and code. Third, the two-stage paradigm. Unsupervised pre-training followed by supervised fine-tuning and RLHF alignment turns a raw predictor into a helpful, honest, self-assistant fourth scaling. Loss revealed predictable performance gains and surprising emergent abilities like few-shot reasoning and code generation. Fifth, real world application span content creation, code, customer support, and multimodal AI, while hallucinations, bias, safety risk require ongoing guidelines. So, GPT is much more than just a chatbot. It represents a major step in how machines understand and generate human language. From predicting the next word to producing meaningful and context aware responses, GPT has transformed the way we interact with technology. Of course, GPT still has limitations. It can make mistakes, generate incorrect information, and does not truly understand the world in the same way humans do. But its rapid development shows us how far language models have come and how much further they may go. With that, I would like to conclude my presentation on language models GPT. Thank you for listening.